this Euler equation, if we rewrite the Euler equation, we can write down like this way. Because it's a steady flow, so we only have a convection term. And this convection term, the right hand side, the gravitational force, basically is the body force. And this body force, we can use a potential function to represent this kind of body force. This usually is in the potential field. You can use this kind of potential function. So, like the electricity field or the magnetic field, this kind of a field, if you have this kind of force, in many cases, you can regard this in this kind of potential field for the body force. Okay, so for this case, we only use a gravitational force to use a potential function to represent this kind of body force or potential force. Okay, and for this equation, you can see the right hand side. Basically, they are gradient potential function and the gradient of pressure. If the left hand side, we can make this become to some gradient, then we can integrate whole equation. So this part, if we make the gradient, it's like we rewrite this this function become to this function. Okay, so you can see for the convection term, for the this convection term, then we can rewrite like the gradient of this term, and also the vorticity and the velocity of their curve. This part, I will give you to do the homework. Okay, so because if you know the index notation, you should be able to do this. Then you can see this rewrite as a kinematic square, and also another term is a two-vector curve. This is a gradient, same as potential energy and pressure. So we take this gradient to the left-hand side. So original term, like this term, we will take this term, combine with the potential function and also the pressure. So we can get this term. This is for the potential function, this is pressure. And after we write this term, then we have this kinematic energy square. So basically you have a gradient, and then we follow the particle velocity. So basically you can see this is some kind like a convection term. They follow the straight line. Okay, so follow the straight line, that means this should be certain of a result, like a velocity curve, this vorticity. And velocity curve, vorticity, basically they will perpendicular to the velocity direction, right? This curve basically perpendicular velocity and perpendicular to vorticity direction. So if you dot velocity or you dot the curve, either way they will become to a 0. Okay, but right now we are dot the velocity. So this term, because they must perpendicular to either one, so that's why right hand side become to a 0. Make sense? Okay. And this term basically is a convection term for the total energy, because the kinetic energy, potential energy, and the flow energy. So this term is for the steady flow. Now we become to a certain level of constant. we can see this term basically is this Lagrange differential term, their convection term. So that means if we follow the particle, the same particle, if they go along here to here, then basically this term will converge, and will be constant. Then, if the steady flow, that means any particle goes through this point, that will be the set. Okay? So, under the steady flow, basically partial T, no matter which particle goes through this point, they should keep the set. So, we will get a convection term. If they along the same straight line, if they along the same straight line, this value we converge, then they will be the same value because after the gradient, they will come to a zero. Okay, so that will be the simplified momentum equation. Use the Euler equation, we can get the Lagrange equation. Same as your undergraduate result. So continue the Gaussian equation for the Gaussian equation, the last Gaussian equation will be the energy equation. And the energy equation is the scalar equation. Basically, it's only the one equation without the direction. But you can see the heat flow and the work. Basically, they have a direction. So it's like converge the direction into the scalar. So for the energy equation, we are consider the system total energy in a different state. Then this is due to the heat and the work. Heat and work basically is the test function. Depending on what kind of test function, you will get the final state. Okay? So in undergraduate, usually in thermodynamics, I will tell that you come into this university, then what kind of your energy will change. Is we only see you come in which kind of state, come out in what kind of state. And the path will depend on how you choose. You choose what kind of a path will increase your own energy. Okay? And for this kind of condition, total energy, basically we can consider as internal energy, kinematic energy, and potential energy. For this energy, basically they are considered with temperature difference and pressure difference for this kind of internal energy. The other, these two, we become to the external force. For example, like the gravitational force or your pressure, they will change about this kind of energy. So basically, this energy can rewrite for the open system. We can rewrite as pressure. For this energy, usually we can rewrite as the internal energy and the pressure. Pressure, velocity, and gravitational force. You can see this term, we become to the Bernoulli equation. So in the thermodynamics, they are talking about if you don't have a temperature change, internal energy will not change. Your pressure, kinematic energy, and potential energy, they will change as the mechanical energy without temperature difference. So similar like the Bernoulli equation, if you only have a force. Later on we will show that if you only have a force, this equation will become to a Bernoulli equation. Because this term doesn't consider, you don't have a temperature difference. Pressure plus kinematic energy plus potential energy. Same as Bernoulli equation, the total energy. Then if we consider separately the heat is due to the temperature difference and the work is due to the external force. So if we write down that component like the heat is by the Fourier law, so we can write down like this. Basically, here I use a dot is to represent the rate. For example, like this is like a rate, And the sum of a gradient is for the space. So you have a time variable and you have a space variable. So for the rate, we usually use a dot to represent. In the textbook, they don't use this. They just use a small q to represent the time. But you just need to distinguish the difference, okay? And for the work, this kind of sketch is write down like the figure 2.2 in the textbook. For the work, they are due to the service force. So for the service force, if we want to see the work, that will be the force times the velocity, okay? And this velocity should be same as the force direction. So just like we mentioned before, this force direction and the velocity direction, for example, this will correspond to the force direction, and the other will correspond to the service direction. Okay? Here, they will use the same notation like the textbook previous definition. This is different from the Navier-Stokes equation. So in the Navier-Stokes equation, this index will a little bit different. Okay? It's just like a first hour we talk about the Navier-Stokes equation, that the index. Then we use another case. Then we use something like the J for that. Okay? So you maybe look the previous note we are talking about. But here they use consistent because the velocity consistent with the second index. But for this case, for the work, because the work is a scalar, so both I and J both are dummy index. The final result, we just get the scalar work. Okay? So for this case, we will convert vector become to the scalar. So for the work, you can see we will diverge about this work because they are considered these two differences. Then they will let into the control model. Then for this work, you can see they have a velocity and the service force. Both are function of x, y, z. So in this parenthesis, the two parameters need to differential separate. And I believe after the index notation, you should be able to do that, right? This is a function of z. This is function of x and y. So iz both are some kind of component. So if you separate this, you shall have another two terms, right? You shall keep this, differential this, and also keep this term, differential this term. Okay. So this is another vector identity. Substitute that into this equation, then we can write down the energy equation. Then you can see what the component for this service force. We have a pressure, we have a shear stress. Pressure with contribution to the conserve for the energy. So pressure with contribution to here. Then we become to some kind of energy. They can change with the kinetic energy and also the, yeah, I know it's the time. He's quite rushed to get over the class. This three will be convertible, but another new term, viscosity. Viscosity with contribution to the thermal energy. So then we make a not mechanical energy, useful mechanical energy, reduce. So that's why we have head loss. The head loss is due to the viscosity force. So next week we will talk about how this force will become to reduce useful energy for the mechanical energy, and that function is referred as Poisson dissipation function. And Poisson basically is the scientist all lifetime trying to solve this equation, but he didn't succeed. But in his lifetime, he finds some energy we lost. So that's why people use that to remember this contribution with the Poisson dissipation equation. Okay? So we will talk about next week. Will you come next week?